We are going to finish a couple things about energy and power and then start in with linear momentum and talk about that today. So getting started, one of the last things with energy, with gravity, the first gravitational equation we learned was the force of gravity is equal to mg. Now forces are vectors, so I'll put my vector sign there. It's in the direction of g. We define down as the direction of the force of gravity. So the g vector is 9.80 meters per second squared down, and the force of gravity is that. But that force of gravity is actually an approximation for when you're on the surface of the Earth. Isaac Newton was the one who determined that the force of gravity is a constant, m1, m2, over r squared. Now notice it's not a vector yet, so I'm not done. So the magnitude is that constant g multiplied by the mass of one object times the mass of the other object, divided by the separation of the centers of mass squared. And this is always attractive, so we put things like a minus sign and an r with a hat over it to indicate the direction is the attractive direction between the two. So those two equations have to be equal to each other if what we've been using in class is right and if Isaac Newton is right. And of course, if you want to get all kinds of technical, it's actually Einstein gives us a different understanding, but for all practical things, we'll take Newton's laws, right? So I think I went over this, but I'm not 100% positive. How can those both be correct? Since nobody blurted it out, I'm going to guess I may not have gone over it. Well, they're both correct, Jonathan.
If you ignore the significance of one of the masses and set r to a constant.
Okay, that's almost right. If you don't ignore it, but you set mass 1 equals the mass of the Earth, and r equals the radius of the Earth. Because everything that we do in our daily lives is pretty much on the surface of the Earth. And the surface of the Earth is almost 7,000 kilometers from the center, if I recall my numbers right. And so even if you climb up to the top of Long's Peak, how much have you gone up? Compared to the radius of the Earth, virtually nothing. So the variations in elevation we have are very small compared to the radius of the Earth. So we can treat those as constants if we're on the surface of the Earth. And so if I put those into this equation, I get this here becomes that, and so this term in the parentheses is g, the acceleration of gravity. So we're treating that as a constant, which is pretty much what Jonathan implied. So that equation, force of gravity is mg, only applies in the surface of the Earth. So if you're in a spacecraft orbiting the Earth, you can't use force of gravity is equal to mg and g is 9.80 meters per second squared down. If you're orbiting the Earth, the acceleration of gravity is still there, but it's maybe 80 to 90% of what is on the surface of the Earth, depending on where you're orbiting. Now, of course, that brings up another question that everybody knows. If you're out in space, you're weightless, right? You what? Okay, as long as there's no gravitational forces acting on you. Well, when we say that an astronaut feels weightlessness, what's actually occurring is they're in a spacecraft that has an acceleration of gravity that's pulling it toward the Earth. And there's an acceleration of gravity pulling them toward the Earth. They're going in the same circle at the same speed. And so the acceleration of gravity is exactly equal to their acceleration in that case. And so they're both sitting there just accelerating toward the Earth, changing direction. And the spacecraft is accelerating the same as they are. And so as far as they can tell by looking at the spacecraft, They're just floating around inside of it because they're both falling to the earth the same way. Now, I say falling to the earth because they're accelerating toward the earth, but they're not getting closer to the earth because they're moving horizontally. And so that acceleration toward the center of the earth is just changing their direction to make them go in circles. And of course, you would also feel weightless if you were in an elevator and everything broke and it just fell, right? Because the elevator would fall down with the acceleration of g. You'd fall down with the acceleration of g. You'd feel weightless until the elevator hit the ground. Then you wouldn't feel weightless. You'd feel very weighted. So that's our force of universal gravitation. It's really important in astronomy, right? We can't do astronomy without that because it's that force of gravitation that causes matter to be pulled together to form nebulae, to form systems of stars like a globular cluster, to form a solar system, to form planets. All of that is governed primarily by the force of gravity. The force of gravity is always attractive. I think I mentioned yesterday, we only have one kind of gravitational charge. We call it mass. Only one kind. It's always positive. Gravitational force is always attractive. So you're attracted to everyone in this classroom. Now, the strength of that attraction depends on your mass, their mass, and how far apart your centers of mass are. So if you were to take, two people sitting next to each other, Brandy and Jonathan, their separation is about 1 meter. Their masses, we could approximate and say they're each 100 kilograms. Clearly, they're less than that. But we could approximate to say that they're each 100 kilograms. And then we could calculate the force. But we have to know G. G is 6. Boy, I think that's right. I didn't look it up before class.
What is G again?
It's the gravitational constant. It's just, notice this is capital G. I know it looks like a 6 here. Does that look less like a 6? Maybe. It's a gravitational constant. So it's a constant. It doesn't vary ever, at least according to our theories. And so if we take this and we said each one of those two has a mass of 100 kilograms, 100 times 100 is 10 to the fourth, divided by their separation of 1 meter squared, means I'm just going to take this number and multiply it by 10 to the fourth to get their total force attracting each other. So if we multiply that through, that's going to be the force of Brandy on Jonathan is equal to 6.67 because of bad planning. I'm just going to erase it and start over where I have more room. So that's the mass of the two divided by the separation of the center of masses squared minus 11 plus 4 is minus 7. I put 2 minuses there. 6.67 times 10 to the minus 7th newtons. Now, just for comparison, this here is 1 kilogram. So the force that it puts on my hand due to gravitation from the center of the earth is 9.8 newtons, or more than 10 million times the force between Brandy and Jonathan. So Brandy and Jonathan don't notice that there is an attraction due to gravity between them, just like none of us notice attraction between us and somebody else due to gravity because it's so small. But if you have really large masses, like the mass of the earth, the mass of the sun, then that force becomes really large because it's proportional to the product of the masses. It's always attractive, so at large distances, this is the dominant force because the other forces that are long range, the other force that's long range, electromagnetic force, we have positive charge and negative charge, 2 types of charge, and it can be attractive or repulsive. Averages out to 0 if you have a large amount of particles. But with gravity, it's always attractive. The more mass, the stronger it is. You got a question, Colton?
When you said size, does that include something that's just really dense as well, right?
Yeah, the mass is what I'm talking about there, yes.
Sorry.
Okay, so that's the other force of gravity. That's the force of gravity that always works unless you have relativistic concerns, you're worried about the curvature of the space-time. If we use that force of gravity and calculate our gravitational potential energy, we're obviously going to get a different equation. So if I graph, well, here's the potential energy function. This is the potential energy that you have between two masses that are separated by distance r. And when you look at it at first glance, it looks like it's just the same as the force, but it's not. What's different about it? Negative. Well, now when I had the vector for the force, I had the negative sign, but it has a negative sign. That's something you notice.
It's not r squared.
It's not r squared. That's the significant difference that I see. It's gm1m2 over r instead of gm1m2 over r squared. Now, it would be simple but untrue to say, so because work is force times distance, I just took my force, gm1m2 over r squared, and multiplied by distance r. But we didn't have that motion of distance r, so that's not what we did. And people in Physics 251 can tell you, we worked this out in class yesterday. It's just done by integrating. But the potential, notice U here. U is a common symbol for potential energy. Question, Jordan.
So why is it r and not r squared?
Because when you integrate dr over r squared, you get minus 1 over r. So that's why I didn't go through the math of it. Got to integrate. So U is just a way of saying potential energy. Our textbook uses PE, at least I believe from my review. And so that's why I've been using PE. So if we graph that potential energy, it's always negative. And as radius approaches 0, that is if you get two objects really close, the potential energy drops toward minus infinity. If they get really, really far away, it goes up towards 0. So we set our reference point of potential energy is 0 if the two objects are infinitely far away. Anything closer and it's negative. Now, one thing that can be confusing is if I take this pin and I drop it, it goes down. Why does it go down? Because it has a force of gravity. We can talk about it in terms of energy, though, as well. It has a gravitational potential energy, and I let go. It naturally goes to a lower potential energy state. That's what things naturally do. You can talk about the motion of things in terms of energy. Things naturally go to a lower potential energy state. Or you can talk about the force, because the force and the potential energy are inherently connected. So they're just two different ways of saying the same thing. So, of course, we understood the potential energy to this due to gravity, I said, was mg times the elevation. So if it's going to go to a lower potential energy, it's going to go to a lower elevation. Makes sense. Just to finish this thought before I move on, where does the energy go when I drop it?
Into kinetic energy.
Goes into kinetic energy. When it hit the table, it bounced off, hit the floor. You hear that sound? That's also energy that left it. So it was converted not just into kinetic energy, it was converted into kinetic energy, then it hit the table, converted some into heating, some into sound. The energy wasn't destroyed, but it went into something else. Now, if we use this new equation, it also has to be true. What's happening to the radius, that is the distance from the pin to the center of the earth when I let go? It's getting smaller. And so if we look at gm1m2 over r, the magnitude is getting larger because we're dividing by a smaller number. And at first blush, that seems wrong. Potential energy went up in magnitude, but its sign is negative. And so that actually was going down. So the potential energy goes down in both cases. Sigh of relief. Maybe you guys never had that concern, but I did at one time. I had to sit down and think about it. And then, of course, I said, well, duh. Okay, one more thing on this. One last thing, I think. When we talk about energy like this pin, we usually say this pin has this much potential energy. If I throw, okay, I won't throw the pin. If I throw this, Brandy? If I throw this at Brandy, hopefully, unlike when I swing around the head, it'll go to her. Where was the kinetic energy while it was traveling through the air? What possessed it?
The ball.
The ball did. Okay, so it's easy to identify the ball had the kinetic energy when it was thrown. And as she's holding her hand, the ball has potential energy. Almost. The potential energy is not of the ball. It's between the ball and the other mass that it's interacting with significantly. What mass is that ball interacting significantly with? It is with her hand, but it's not significant. That force is really small. The Earth. And so the potential energy, the gravitational potential energy, is not held by the ball. It's not held by the Earth. It's held by the system of the two. So then we can take things and say, well, I have this mass. I have this mass. The potential energy between the two is, minus g times the mass of this times the mass of that divided by the separation squared. What if I bring a third mass into the equation? So I have one mass there, and I put a third one here. How do I calculate the potential energy of this configuration?
Mass 3.
The 3 what? Okay, I didn't quite hear what she said, but here's what you do. You have potential energy between each pair of masses. So you calculate the potential energy between these two, plus potential energy between these two, plus potential energy between those two. And that's going to give you the total potential energy. Because potential energy is the interaction between a pair. It's not held by one object. And so I can't say, in this configuration, the potential energy of this one is X, right? Because it doesn't hold it. There's potential energy between these two and potential energy between those two that it's involved with. Power. Question.
You said that there was potential energy between the two and the two, but would there not be an interaction of all three together, or would there be?
The potential energy, well, if you want to be all kinds of technical, the potential energy is between each piece of mass and every other piece of mass.
Right.
For general physics level, we treat each one as if it's just a point.
Okay.
And then the potential energies between this point and that point, this point and that point, and that point and that point. So it's associated with each pair that you can make. Like I said, if you want to get all technical, well, it gets a lot more complicated. Jordan.
So kinetic energy can be held in one like the ball, but but potential energy can't be held by just the ball.
That's right. Okay, power. Power is a simple definition that by the time we get to second semester, people often forget. And so we start talking about power again, and people are like, something to do with energy. Power is the rate that energy is converted. It's a rate. It's energy over time. So I have here power is equal to work over time, because work is a conversion of energy process. Or I have delta E over time. It's a transfer of energy. It's a conversion of energy. So if we look at units, what were the standard units we used for energy? Joules. So for energy, we had 1 joule equals 1 Newton meter equals 1 kilogram meter squared per second squared. Now for power, we divide that by time. So that's going to be 1 joule per second, or 1 Newton times a meter per second, or 1 kilogram times a meter squared per second cubed. And just like I said, seconds squared are meaningless, seconds cubed are equally meaningless. But in the unit for power, it means that you have energy per second. And because power is very common, we have a unit for that is the watt. So 1 watt is 1 joule per second. That's the standard SI unit for power. What does that show? The one where you have lifelines? Okay, who wants to be a millionaire? Or yes, I don't know. There's a picture somebody took of a contestant, and the question was, this unit of power equal to 746 watts is given the name of, and it had something like zebra power, horsepower, donkey work, things like that. And the guy had to use the audience poll because he didn't realize that horsepower was a unit. It's kind of sad because zebra power, really? Yeah, my car's got 150 zebra power. Barely gets. If it was horsepower, I'd barely get down the road. But 150 zebra power, that's a lot more. The horsepower is an English unit of power. That is the imperial unit. So that's the one that's based on, a foot-pound for the work and then divided by seconds. So horsepower is supposed to be calibrated to be how much power a horse puts out. What horse? I don't know. So power, the rate at which energy is done. A very interesting thing here, if you looked at the units here, the units were force units times speed units. And since work is force times distance, it actually works out that is another way to calculate power. Power is the force applied to something times the speed at which it's moving. And notice those are two vectors with a dot in between. What does it mean that they're two vectors with a dot in between? Yeah, I heard some people say dot product, and Jordan got halfway through. You multiply the parallel parts. So this would be equal to the force parallel to the speed times the speed. So power can also be related to that. Now, I had a student ask me a question. It was actually from one of the concept coach questions about power of something. Like, let's say you have, a vacuum cleaner that, I don't know how much power a vacuum cleaner uses, so I'm going to go with a light bulb. You have a 60-watt light bulb. 60-watt light bulb means that it's using 60 joules per second. And so the question was about, so you have it didn't say 60 watt, but you have a 60-watt light bulb, and let's say you observe it for 10 minutes. What's the power after 10 minutes? It's the same, because the watts is the rate at which it's using energy. If it asks you how much energy did it use, then you would say, power is the rate it's using energy, so the energy would be energy used, delta E, is equal to power multiplied by change in time. So that would have been 60. My hand gets ahead of my brain. Once again, my hand went ahead of my brain. 60 watts multiplied by how much time? I say 10 minutes. 10 minutes is, I can't put in 10 minutes, wrong units. It's 600 seconds. And so that would be 36,000 joules that it would use in a 10-minute period. Now, if you get it, probably most of you don't deal with electric power bills, but if you get your electric power bill, what units does it list your power in? It usually is in kilowatt hours. So, it might say your energy usage this month was, let's make up a number, 84 kilowatt hours. What would kilowatt hour mean? What type of quantity is that? That's going to be, I didn't hear what you said, Colton. Sorry. That would be energy. It's energy because kilowatts are units of power, which is energy per time. So energy per time multiplied by time is energy. And so you can calculate how many joules that is by saying, that's equal to 84. I heard the people across the hall doing their practice for the ham radio test yesterday, and they had questions like, so 3.25 megahertz, how many kilohertz is that? Hopefully you guys are good with these prefixes by now. So kilo means 1,000. And an hour is 60 minutes, a minute is 60 seconds, so that's 3,600 seconds. And so if I just multiply those two numbers together, which I asked my trusty calculator bearer.
Let me see.
Can I-
302,400,000.
So 84 kilowatt hours is millions of joules. And so the unit is something that's actually easy to calculate because you can say, I have a computer with a power supply that uses 750 watts. Now, it's not continuously using 750 watts. That's the maximum it can produce. If I use this computer for 1 hour, that's 750 watt hours. You can do the calculation real quick. That's why they use those units. So that's our power thing. You should be able to do any calculation with power pretty simply because it's just energy per time or force parallel to speed. So now let's get to, I think this is the last thing on work. And yes, it's a clicker question. It's not open yet. But then again, nobody's ready to answer yet because you haven't read it. So this is a true, you guys have probably seen Ask Marilyn. It used to be in like the Parade magazine every Sunday in the newspaper. She is the person with the highest measured IQ ever. Her husband, by the way, is the inventor of the Jarvik artificial hearts. Anyway, so she was asked, which requires less work, taking 2 bags up 2 flights of stairs at once, you're just lugging up the 2 bags, or taking one half, up 1 flight of stairs, set it down, going down, getting the other one, taking it all the way up, setting it down, going down halfway, getting the first one, bringing it up. Which one's going to take the least amount of work? I like this question because it allows me to poke fun of the person with the highest IQ ever. It makes me feel superior, even though she's clearly smarter than me. Okay, I'll give it about 5 more seconds here. All right. People still coming in. So we had 31 people that said they're the same. 22 said carrying the bags together is less work. And 4 people agreed with Marilyn. So, Megan, can you tell us which one you answered and your reason why?
I said A because they're only doing work when they're carrying the bags, and so it doesn't matter where or when, as long as they're collectively they add the same amount.
Okay.
If that makes sense.
This one here is the correct answer if you're asking about the mechanical work. That is, change in potential energy in this case. Taking the final case, the initial case, it doesn't matter what your process is. It just matters where you start and where you end. So that is what I would consider a correct answer. So now, this is somebody in the Southwest class. Ulana Nwachukwu. I probably said that wrong. Ulana, did you answer something different?
No, I picked A.
You picked, okay, then I'm not going to ask you. How about Alyssa Rhoda? Or Alyssa, probably.
I picked C.
Excellent. Can you explain why you picked C?
I picked C based on experience.
Okay, I'm going to rely on Thomas here. What'd she say?
Based on experience.
Based on experience. Okay. Okay, based on experience, that's reasonable basically you're going to feel more tired if you had to do that because your body had to put out more energy because each step you're starting and stopping, right? I mentioned this before. So this one here would be energy expended by the body. And Marilyn Vos-Savant said that carrying the bags one at a time is less work. And I was like, what in the world? Now, I was in graduate school, so I was all kinds of feeling superior at that point in my life. And I was like, how in the world could she get the wrong answer on this? And her response or her justification of why that was the least amount of work was she said, well, if you're carrying the 2 bags, you're going to be less winded when you're done. And so that means it was less work. And I'm like, she obviously doesn't actually know what work is. Work isn't a measurement of how tired you are. If that was the case, if we were to take, Usain Bolt running the 100 meters, and, those guys after the 100 meters, those guys pretty much collapse. It takes them a while to get back. Or we take somebody who runs the marathon. I'm sorry, I can't name a marathoner off the top of my head. And you'd say, well, the marathoner is not as debilitated at the end of the marathon as the sprinter is. Those guys can still walk it off, basically. Obviously, the marathoner did a lot more work, but the power output was much less. When Usain Bolt is sprinting, the power that he's putting out is incredible. So he's putting out a huge amount of energy for a short time, and he gets really tired. Whereas the marathoner is putting out a much smaller amount of energy. Now, if I was a marathoner, it'd be a high amount for a very long period of time. So it's a lot more energy, but a much smaller power. And you can keep up your anaerobic zones if you can run a marathon when you're doing that, whereas the sprinters are in an anaerobic role. Their bodies can't keep up the energy output they're doing. Okay, now we get to a new topic, momentum. So the question here, once again, I got to move this forward so you can answer. It would be accurate to say that the Manchester City soccer team, the European Premier League, currently has a lot of momentum. It is accurate. They're undefeated so far this season. Play this afternoon at 1:45 in the Champions League against Celtic. Okay, so which of these statements is a correct statement that matches what that means? All right, give it about 5 more seconds here for the last people to get their answers in. And what we ended up with was 4. That's a 4. 49 and 1. So there was a large majority that said that they are hard to beat. So, Hannah, were you one of the people that said that? What was your reason to say that by saying that Man City has a large momentum, they're going to be hard to beat?
That they could go for longer at a certain rate.
Longer at a certain rate. We haven't studied momentum yet, so I was looking for people's perceptions. That doesn't match mine. When I think of a team having a lot of momentum, and I was going to put in the Denver Broncos, but it just hurts too bad to say Denver Broncos have momentum. What you mean is they're going to be really hard to beat. They're on a roll. Kind of like when Blutarsky is talking about the Americans didn't stop when the Germans bombed Pearl Harbor. And of course, I think it's odder questions. The Germans? It's rolling. So was that a question?
Your sound is going kind of like off and on. It went out for a second.
Really?
He's having connection issues too.
Actually, yeah, that could be because your screen has been freezing periodically. Like right now, it's frozen.
And it's just going out again.
Exactly. So yes, it's definitely connection issues. While it was out, your screen was completely frozen. Which way the connection problem is, I don't know. We're not using Polycom, so it's not that problem. So getting back to the momentum then, when something has momentum, it's going to be hard to stop. And that's what we mean in physics about momentum too. Momentum is going to be something that's hard to stop. We have an equation for momentum. Momentum is, first, P is the symbol for momentum. Why? I honestly don't know. I guess if we'd probably go to Latin or something, we'd find a reason. But momentum is the symbol P. It's a vector, so I have the vector sign over it. It's mass times the velocity. So it has a direction, it has a magnitude, the mass times velocity. If something has more momentum, it's going to require more force to stop it. In fact, I'm right now going to look at Newton's second law. Newton's second law said that the net force equaled mass times, that's not mass, mass times acceleration. But I could write acceleration, the average acceleration is mass times change in velocity over change in time. Or for an instant, the instantaneous acceleration is the instantaneous change in velocity over change in time. Well, if we look at this definition of momentum, if the mass is constant, this is going to be mass times speed final, velocity final, minus mass times velocity initial, all over change in time. But since momentum is mass times velocity, then we end up with the force net is equal to the change in momentum over change in time. And this may surprise you. This is actually Newton's second law. Newton's second law is that the net force is equal to the change in momentum over change in time. And it's, of course, really a calculus equation. It's really equal to the derivative of momentum with respect to time. But this being an algebra-based course, we don't worry about the calculus, and we just say change in momentum over change in time. So momentum relates to force and the time it's going to take to stop something. So if something has a higher momentum, it's either going to take more time to stop it or it's going to take more force to stop it compared to something with a lower momentum. As you might have guessed, when I talked about energy, I talked about, if Gila and I were running at the same speed, which one's going to be harder to stop. And I was talking about energy in terms of stopping. Energy and momentum have often had some confusion because they both are going to relate to the stopping or starting. How hard is it to start? So momentum problems, we often deal with things like shown here, a collision between two vehicles, what happens? So momentum is sometimes conserved. It's not always conserved. Now, remind me, you're, senile teacher, what does conserved mean in physics? Okay, for energy conservation, it meant that the energy wasn't created or destroyed. So if I apply it to momentum, if momentum is conserved, that would mean that it's not changing. Now, if we look at Newton's second law here, what condition would have to be true for the momentum to not change? That's the one I didn't expect you to come up. It is a reliable answer. You can solve that equation to say change in momentum is equal to the net force multiplied by the change in time. So if there is no change in time, momentum can't change. In automobile collisions, the time of impact is really short. And so we approximate that delta t is 0 during the collision between two automobiles and say the momentum that the two automobiles had just before the collision is equal to the momentum the two automobiles had just after the collision. So change in time equal to 0 is one of the two conditions. It's not the one I expected people to answer because I had it as force net is changing momentum over changing time instead of this way. What's the other condition that would result in no change in momentum? If what?
It's the same force.
Okay, we have to be a little clear on what you mean by that. You're right. We have to be clear on what it is. She says if it's the same force. If the net force is zero, so if there are two forces acting on an object, if those two forces add up to zero, its momentum won't change. Now, when we take something like, well, if two automobiles collide and there's no friction between the automobiles and the ground, we could take the momentum, a minute before the collision and compare it to momentum a minute after the collision if we consider both cars as our object. Right? If we consider both cars as our object, then I could just say the momentum before is the momentum after if there's no friction. But of course, there's going to be friction, so we can't do that. So when we're looking at situations with momentum and asking, is momentum conserved, we have to consider these two considerations. If we have a collision, we'll always say, well, the time of the collision is very short, so during the collision, momentum was conserved. There's actually another thing going on with collision. If I have a collision between two cars, during the time that they're actually crunching, the force of one car and the other is really large compared to the force of friction during that time. And so we can say the force of friction is also negligible during that time because it's so small compared to the force. So there's two reasons to say during the collision, momentum's conserved. Not before and not after. So if I have a car that's parked and another one comes skidding up, what's going to be happening to the energy of the car that's skidding toward the stopped car? It's decreasing because friction is doing work, taking away energy. Its speed is decreasing, its momentum is dropping. When it collides, then we'll say during the collision, momentum's conserved. And then after the collision, both cars go sliding off, and we'll say, well, momentum's not conserved there. How do we use this? Well, let's say you are a police officer. Back when I was at PHYS, I was on the volunteer fire and ambulance, and we'd have to respond to car accidents. Police officer shows up, and by the time he gets there, we've already got everybody extracted and whatnot. So first thing he does, say, you guys got everything under control? Good. He gets out his wheel and he starts measuring the length of the skid marks. He's measuring the length of those skid marks so he can calculate how much work was done by friction before and after the collision and calculate the speeds of the automobiles at the time of collision. Right? So they're using physics calculations there to try to extrapolate from the evidence that's on the ground how fast they were going. So, you know who to give a speeding ticket to or whatever. Okay, a very true story. An 80-kilogram man and a 40-kilogram woman are on ice skates. If the 80-kilogram man carefully pushes the I changed numbers. 40-kilogram woman, so he ends up moving backward at 0.25 meters per second. What will happen to the woman? What was that?
So what's the E count to?
I'll tell you when we're done. Okay, I'll give it 10 more seconds here. You can laugh. I discuss this. Okay, let's look at our answers here. We had 2, 19, 27, and 5. So First thing you do when you're doing this problem. If you're doing this problem like on a test, what's the first thing you would do? Draw a diagram. So you'd have, here's the dude. And here's the dudette, the chick, whatever. And what's their initial velocity? Both at 0. So I'm going to put V chick initial equals 0, V dude initial equals 0. I'm going to decide that my positive direction is this way. Got to decide which direction is which. Now I'm going to make my after picture. So that's my before picture. My after picture, I have the dude is traveling backward. And I got to figure out what's going on with the chick. So now 5 people said that she's there. I don't like those 5 people. Nothing personal. Everyone else said something on the order of she's moving. So in order to answer this, I need to first think about what concept's going on. I've drawn my picture. Now it's time to think about my concept. We just started a concept. It's pretty easy to nail it down, but keep in mind, our next test, we're going to have Newton's laws. We're going to have work and energy. We're going to have rotational motion. We're going to have momentum. That's the end. This is the last chapter that's going to be on the exam. So you'll have to go through all of those ideas, and which idea do you come up with? Jonathan?
Newton's third law.
Okay, Newton's third law can be used. You can use Newton's third law in conjunction with Newton's second law and solve this. So that is one way. It's the longer way, but you know what? If it's on the test and it doesn't say use this way to solve it, that's perfectly legitimate. Okay? What's the preferred way I'm trying to get at? Momentum, right, because it's in the momentum section. So if I use momentum, I have to ask myself, is momentum conserved? If momentum is conserved, then I do it one way. If it's not conserved, I do it another. So is momentum conserved here? They were on ice skates. The ice skates is supposed to illustrate to you that they're going to have their feet parallel to each other and going to have virtually no friction, which means the net force is 0. And so the problem is worded to give you the impression, the correct impression, that the force net on the system of the 2 people so that means momentum of the system is conserved. So just like with work energy, if momentum is conserved, I'm just going to take the initials equals the finals. So I'll have momentum initial is equal to 0, right? Because they were both stationary. I don't need to put m1 times 0 plus m2 times 0. Momentum final is mass of the dude, speed of the dude final, plus mass of the chick, speed of the chick final. Put in my numbers. Well, actually, let's solve it for the speed of the chick first. So if I solve that for the speed of the chick, we're going to have speed of the chick final is equal to the mass of the dude times the speed of the dude final over the mass of the chick. Okay, I should have put a minus sign there with his velocity speed because it's actually, we have velocities in one dimension. That was the negative direction. Minus 0.25 meters per second times 80 over 40 gives me, oh, I forgot a minus sign there. Minus sign there makes it a plus. Forgetting things today. 0.50 meters per second. So she's moving out here at 0.50 meters per second. That's the way it's supposed to work. Here's the textbook problem. Here's the reality. Sadly, I was very careful. I said, now, Nalko, we're going to push off each other, and because we're different masses, blah, blah, blah. And she fell down, and then she got really angry at me. Very, very bad day. And then after we finished the ice skating, I took my skate off, and one of the skates was filled with blood. Really, really bad day. I looked at my foot. My foot was nice and fine. Somebody else had used the skate before me because it was a rental, and they had bled like a fin in there. That was a great day, I tell you what. Okay, we're out of time, so we'll stop right here.